Okay, so let's talk about Flamingo. Flamingo is a visual language model for few shot learning by DeepMind. We will go through its architecture, how do they train the model, and also go over through the code, how it works. So all the three things we will do. Flamingo is a family of visual language models, and in this paper what they do is introduce its architecture, the data set that was used, and the evaluation of this model. So what this model can do is few shot learning. So for example, this is the input to the model and this is the output. So if we give this input along with the text, this is chinchilla, and this is a Shiva dog, and then if we give this query image, then it completes it. This is, and the model completion, this is a flamingo found in Caribbean and South America. Another example is this simple math problem. We give it an input image and also show what the output should be. So 2 plus 1 is 3, 5 plus 6 is 11. So it comes with an image and the input text, and then we give it a query image 3 multiplied by 6, and the model completion is 3 multiplied by 6 is 18. So it is also able to understand images as well as text. Now directly let's go to the architecture of the model, how it works. So this is the overall architecture of Flamingo, and what it can do is take arbitrarily interleaved visual text data. So interleaved visual text data means, so if you're reading for example this paper or any web page, there are images like this figure and there is a text corresponding to that image. So, and there are multiple images and multiple text, right? So the model should be able to get an input image, its corresponding text, and the output from this model is text. So for example, if we give this input image, this is a very cute dog, and also this image, this is, and the model should be able to complete this sentence, this is a very serious cat, right? And how this works is the input images goes through a frozen vision encoder. We will be using vision transformer for vision encoder, but we can use any other also. Then it passes through a receiver resampler, and what the purpose of receiver resampler is to decrease the number of visual tokens. So for example, there can be arbitrary number of, so the input images can have arbitrary resolution. So this encoder will also produce different size of visual tokens and features. And the purpose of perceiver sampler is to downsample it to fixed number of visual tokens. It makes it more easier for model to ingest this fixed number of visual tokens than to have this variable number of tokens. Right, so what happens is in place of this image, we introduce a special token called image token, and I will show in the code how this is done. And then this is the text, and this image gets encoded by a vision encoder and perceiver resampler. And this is a pre-trained LLM. It can be any LLM, but for our experiment we will be using opt 125 million, so openly pre-trained transformer from Meta. The layers of LLM are frozen, and what we do is we insert the gated cross attention layers in between these LLM layers, and these are learnable, right? And what they do is attend to those visual tokens so that this model overall becomes multimodal instead of just inputting text and understanding text. In this gated cross attention and attending to these visual tokens, this model becomes multimodal. Now directly going to the approach, so this is the objective that they are trying to model, so which is basically the probability of these tokens from L1 till L given the previous text token and be given the previous images, right? So if we take this example, so this is the input image, so this will be considered a previous text and previous images, these two. So condition on these input, we want to model the probability of this output text, and the learning objective is to maximize the negative log likelihood of this objective. A little bit into detail of what this gated cross attention does. So this is a standard language model decoder layer. Which includes self-attention and feed-forward neural network, and this is frozen, so we don't train the pre-trained large language model, so we don't forget what it has already learned. What we do is we insert this gated cross attention before these large language model layers. And for this gated cross attention, the query is the language input, and the keys and values are vision tokens, which we get from vision encoder and perceiver resampler. And this input language queries attend to those vision tokens. And it also passes through the 10H gating. And this gating is important. Initially, these gating parameters are initialized to 0. At the start of the training, this input language just passed through this cross attention. There isn't much of an effect from this cross attention. But as the network starts to learn, it gives more importance to the visual tokens, and then it becomes multimodal, right? And the reason initially it's initialized to 0 is that our language model has already learned, it is pre-trained. We don't want to destroy its already learned knowledge. So we want to start slowly. And first, the output of this is just Y. And similarly for this feed forward network, it's also initialized to 0. So this is just passed through here, and then as the model learns, these parameters get values other than 0, and then we can attend to those visual tokens. This cross attention is very standard cross attention given these queries and given these keys and values. These queries again are the language input, and these keys and values are from visual tokens. And we will go through the code what it does. So vision encoder, they are using this NFNet, but we will be using vision transformer trained with clip objective function of contrastive loss. So it's already pre-trained, the models are freely available. This one, I don't think it's freely available, that's why we can't choose. Then they also talk about why we need perceiver resampler, which I already explained. The idea is to have fixed number of tokens. And the idea is very similar to what deter does. It also learned fixed number of objects. For example, by default it's 100, so at most you can have 100 detections, but that parameter or the number of learned queries you can change. And they have this Flamingo model on different sizes, 3 billion, 9 billion, 80 billion. We will be just working with 3 billion, the smallest one. So this is important, how the model attends to images and videos. So we are doing this causal modeling as we shown in the previous equation, that we want to predict the next tokens given previous text and image tokens. So at a given text tokens, the model attend to the visual token of the images that appeared just before it. So if we consider the interleaved image text data, for example this, so we consider that this text corresponds to the image that comes before it, right? So this text can attend to this image before it and not the one that comes which after it, right? And I will show you in the code how it works. So in the cross attention, the text can attend to the image that comes before it rather than to all previous images, and they showed that this works better than if the text attends to all previous images. But if you go into the self attention itself, then it can attend to all previous images, right? And so in cross attention, text token can only attend to previous image, but during self attention, it can attend to all previous images. So this is some data pre-processing. I will go through the code, what they do here. So this is essentially the same as equation 1, except that we have converted the probability to log probability. It converts the multiplication into summation. So again, this is the probability of predicting the token L given all the previous text and image tokens. And we want to minimize this expected value. And we are doing it on 2 data sets. We are doing it on pair of image text. So it's kind of a caption, if you know Coco caption data set. They are using a different aligned data set, which I don't think is publicly available. So we will be using a test Coco dataset to train our model. And what this caption dataset is that we have each image and we have a text corresponding to that image. And then they are also using this M3W dataset, which is more of an interleaved dataset, right? So they have multiple images and multiple text corresponding to those images. And then what this objective does is minimize this objective given on both of these data set. So M is 2 in our case. So we have the interleaved data set and we have these pairs of image text data set. And this lambda is how much importance we want to give to each data set. So they say here that we accumulate gradients over data set which we found or performs a round robin approach. So there are two ways to train our model generally. So if we have multiple data sets, we can take a sample from one data set, do the forward pass of the model, do the backward pass, and that's also called round robin approach. So we go one data set at a time to optimize our model. But here they showed that they accumulate the data set and the gradients over all data set, which this equation is showing. Basically, it says is they take the sample from one data set, do the forward pass, backward pass. Then we take the sample from next data set. We calculate the forward pass, backward pass, accumulate the gradient on top of previous gradients, and then update the parameters. They showed with the 32 shots visual question answering. The Flamingo got 67.6 on test set, while the state of the art is 81%. It is on, well, it has to be noticed that this is purely fine-tuned on this data set, but this is few shot learning. And if you fine-tune the Flamingo model on this data set, then it also surpasses the state-of-the-art model. And there are some other benchmarks you can also see here. This is the perceiver sample module. I think it's good to also go through it. So given a variable length video, we first pass it through a vision encoder. So t is 0 are the different time frames in a video. It passes through a vision encoder and then we flatten it. And then the keys and values become XF, which are the flattened features. And this is the learned latent queries. And this will be the output number also. So going from this many number of tokens, visual tokens or features, we reduce it to this many number of features, which in this our case is 64. Learn latent queries become the queries, and this key and values become XF concatenated with the X, and they showed in the ablation that by doing this concatenation the results improve than just having XF, which is normally the case. It's just one of the hyperparameters here, and then it does this attention from this queries, keys and values, and then this feed forward neural network. I will go to the shapes in the code of what it does. The last thing I want to also show is how the text attends to previous tokens and previous images. I already explained, but for example, if this is the input, right? So we have first some text, cute pictures of my pets, and BOS is a special beginning of sentence token. And then we have EOC token, and then where we want to insert an input image is basically replaced by a special token, image in the braces. And then we have my puppy sitting in the grass, EOC. Then we have another special image token, and my cat looks very dignified, EOC. Right. So first, this text cannot attend to any image because we are doing causal modeling. So it can only attend to any images that came before it. So it cannot attend to any images, and that's what is shown here. Now this text and the color in blue is what this text can attend to. So my puppy is sitting in the grass. This text can attend to this image token, right? And this is what is shown in this blue. So each text can attend to the previous image in the cross attention, and the same goes here. My cat looks very dignified here, and here this text can only tend to the image before it. And again in the code I will show how this attention mask is actually calculated. This is the overall paper. The whole purpose of this Flamingo model is to make model capable of few shot learning given few images and text corresponding to those images. So let's go through the code. So this is my repo Flamingo simple. It is completely based on Open Flamingo. The only difference here is it is really kind of optimized to work on single GPU, and it's mainly for educational purposes. And I have written down the main steps that we go through the model workflow, and we will also run the model to see it actually in the code. But just to connect what we have read in the paper to the actual code, we take here an example of image of batch size 2. So we have batch size of 2, and in each of that batch we have two images of size 3, 24, 24. So two images means that we have interleaved two images. So we have image text and image text for each batch, and the corresponding text input for that will be batch size into sequence length. First, we pass this input image through our vision encoder, which in our case is clip train vision transformer. And the output of that is 4, which is from 2 into 2 is 4, and then that is transformed into 256 is the sequence length or the number of visual tokens, and 1024 is the dimension of those tokens or hidden dimension. Next, we pass this through the perceiver resampler. What it does is downscale the number of visual tokens to fixed number of learned visual tokens. So we downscale from 256 to 64, and this is the code for perceiver resampler. What we have is the XF, which are the vision features. X is the learned latent, where we have 64 is the number of learned latent features. And this X becomes a query, the learned latent, and the key and values become the concatenation of XF and X across the -2 dimension. So what it does is X is of shape 2 to 64, 1024. These are the number of learned queries, and we concatenate XF and X across -2 dimension. So initially it was 256, and we add the 64, so this becomes 320. And then the output shape of attention will be 2 to 64 into 1024, and then we pass it to the feed-forward network, and the output of this is 2 to 64, 1024, which is the same as here. Now, so this is how the vision part is processed. Now, going through how the language is processed. So we are using the language model Open Pre-trained Transformer from Meta, 125 billion. It is the smallest of their models. We add some special tokens in there, right? So we add end of chunk there to determine the end of image text pair. And we also add the image token there, which indicates that the image, this is a placeholder for image in text. And then what we do is we take this OPT 125 million model from Hugging Face, and we add these gated cross attention layers in between this transformer decoder layer, right? So this is how you normally load a language model, or in this case OPT 125 million model. And its original architecture looks like this. The number of decoder layers, here it says transformer 1, 2, 3, and number of transformer layers. And after we do this modification for Flamingo, what we do is we insert a gated cross attention before this transformer layer, so it becomes like this. Each Flamingo layer has a gated cross attention and transformer layer, which is the same as this one. In the code, how it is done is by this function extend instance, and what it does is before the decoder class, it inserts this gated cross attention, and then we initialize the Flamingo model. And this is also how the text is processed. Basically, if we go through the steps, the text goes through a tokenizer, it converts it into token IDs of length 256. We pass it through the embedding layers, which is a lookup table which converts this 256 length sequence into 256 into 768 dimensional embedding vector. We add the position embedding, and all of this happens inside this language model, which is, this is the maximum sequence length it can handle, and 768 is the size of the embedding dimension. So what happens in each step is that we first pass this language X, which is actually the same as input embedding X plus positional embedding through this gated cross attention, and I will show what this cross attention mechanism looks like. And it outputs to 256,768, which is the same as the input, and then it passes through a standard decoder layer of this language model. It can be any decoder based language model, it doesn't need to be only OPT 125 million. It is the smallest model, so we are choosing that. And then finally this language head is passed through the LM head, which converts it into the size of the vocabulary of the tokenizer, right? So we take 2 to 56 76 768, and this maps it through a fully connected layer to 2 to 56 50,267. And finally, one of the most important things in this architecture is the cross attention mechanism, right? So remember, cross attention, what it does is it allows language to attend to vision tokens. So for example, language is batch into text size, which is the sequence length 256, and the dimension of text, which is the dimension of each of these layers, which is hidden dimension 2 to 56 768. And then we have this media. Media is the images, can also be videos. We have of size, in this example 2 is the batch size, number of times or the number of images in each batch we have 2. N is the 64, which is the number of learned queries from perceiver resampler. It can also be seen as number of vision tokens, and 1024 is the dimension of each token. And we also pass the media location, right? So here what we want to do is text token needs to attend to previous image only, like we discussed in the paper. And for that we need to pass where the image token exists in this text. We passed all this information in cross attention. First it does is the X becomes the query, the language becomes the query, and the key and value comes from the image or media. We do some reshaping and rearranging here. And this part is important, how the text can attend to only previous images, right? So first is create a media time, and I've given an example here. Suppose in this example we have 2 images, so media time will be 1 2. So in torch arrange number of the T image is the number of images. So for example, T image is coming from here, so this media time will become 1 2. The text time will become the cumulative sum of media locations, and the media location is where in the tokenized text the image tokens appear. So for example, first token is a placeholder for image, so this is in bracket image. Then we have some text, and then we have another image token, so it shows that in this position we have an image token, and the rest of the positions which are 0 are basically text tokens. And when we do this cumulative sum, so the text time will become 111 because it will be a sum of all the previous, and in this place it will become 2, and the rest will be 2 2 2, right? So this is how just cumulative sum how it works. So we also repeat this media times for n number of tokens. So we also repeat this media times n times, where n is the number of visual tokens, which are 64, same as the number of learned queries for perceiver resampler, right? So this is the 64. So what media times becomes, so media time initially was 1 2, and it will become 1 1 1 1 1 64 times, and 2 2 2 2 2 64 times, right? And then we do where torch equal text time and media time. This token 1 1 1 here and 2 2 2 here can attend to this 2 2 2 here. So what it is actually doing is exactly what is shown here. So since this will become 111 and the text token here is also 111, so this text can attend to all these tokens, and this text can attend to these image tokens 222, right? So the first 3 tokens can attend to the first image because it's a 1 And the first image we mean 64 tokens of the first image, and the 222 means 64 times 222. Last 3 tokens to 10 to second image. And this is how the loss is calculated, right? So we have the logits. We take the entire logits except the last one, so -1 excluding the last one. And the labels are the inputs except shifted by 1, right? So for first token we are predicting the next token, and so on and so forth. And the loss function is standard cross entropy loss. The only difference here is for image tokens and padding and end of chunk tokens, we don't calculate the loss because image tokens are just placeholder. We don't want to predict image tokens. It just shows that text needs to attend to those images at this point. Right, so this is how we train this model. Let's go through the code now step by step and see how it works. Okay, so this is the train function from my repo, and again this is the repo. First, let's go to the create dataset part. And what I did was initially this Open Flamingo model is trained on Leon dataset, which is in billions of images, is humongous. MMC4 dataset, which is also humongous. So I don't have that much storage for storing this much data, and there are other ways to do it also, to have just some shard of that data set. But in this case what I'm doing is to keep things simple. I have Coco data set, so I create this minimal Coco data set, and you can also use this. What it does is just downloads the Coco annotations, and then it creates MMC4 sample. And what it does is it is the interleaved data set, so it takes one image and a text corresponding to that image, and another image and a text corresponding to that image, and then combines all of them together, and then we have MMC4 dataset. It's a minimal example to just show how it works. And again for Leon dataset, I just take single image from Coco dataset and I take a text from it, and I save it as a tar file, which this model expects in Open Flamingo. Or you can actually change the data loader to not just accept tar. To run this, it will create this minimal data set which has only 50 samples. If you look here, we have 50 samples for both of these data set, and using this we can see how this model does the training. And then we can come to this training part, and let me make this bigger. And all this does is set up some, you just need to change this dataset path if you're running it, or actually you don't need to change it because it's the relative path. If you run the create dataset, then it's already there. I only have a single GPU which has a 12 GB VRAM, so yeah, I'm using a smaller batch size of 2. Okay, I have set up some breakpoints just to see, just to show you how this entire thing works. Let's just go through it. We start the debugging and we will go through all the steps which I've already explained, but let's see how this works. It's first set up some configuration. It sets up this model. If we go next, and in this model the vision encoder we are using is from OpenClip, and if we just step through, we are using the vision transformer model. We are using this vision transformer model. We are using pre-trained version of it, and next we are creating the text tokenizer, right? So which is Facebook or Meta opt 125 million. In this tokenizer we add two special tokens, end of chunk, which shows the end of image text pair, and also the image token, which shows the placeholder for the image. Pair token we don't really need because this model already has a pair token, but if you don't, then you can also add this to your text tokenizer. And then we create this language model. So this is a standard interface for creating causal large language models, and it will create this Facebook of 125 million parameter model. So what we have done so far, we have created a vision encoder, we have created a text tokenizer which will tokenize our input text. We added the special tokens here, the image and end of chunk. We created the language encoder, which is op 125, And now what we want to do is comes the main crux of this Flamingo model. We want to extend this language encoder with Flamingo layers, right? And this is done by this extend instance. If we go into it, and what it does is, and this is the main thing what it is doing. This is one way of doing it. It's pretty neat in my opinion. What it does is converts the current object class to mixin and base class. So base class is the language model which we just loaded, and this mixin is the Flamingo layers which it will add to it. So this is a nice neat way of adding new functionality to already pre-trained model, right? So you add a new class and also add a base class to it. So it is adding the functionality of this class Flamingo mixin. And what it is doing is it will init this Flamingo layers. What it does is get the decoder layers, and then it creates the gated cross attention layers, and then it sets the new decoder layers to be first do gated cross attention and then do the standard decoder layer, and then do also gradient checkpoint to save some memory from GPU. So that's all it does. Let's go through the next step. This is just a debugging. I can remove it. This is just to show what is the length of this text tokenizer vocabulary. This is 50,267, and we can resize our language encoder to match this vocabulary. So what it will do is change the first layer, which does the embedding. Since we have added two new tokens here, we have added the image token and end of chunk. The initial vocabulary has increased by a size of 2. So now we need to change the first layer and the final layer of logits to also match this size. And this is what this thing does. Now we go through the model Flamingo, and inside this Flamingo model, it set up all the variables that we have currently set up. It set up the vision encoder, it set up the perceiver resampler. Perceiver resampler does exactly what I explained. It just goes through multiple layers of attention and feed forward neural network, and so it does exactly the same thing what I described before. Right. So it sets up Flamingo, and here it is actually doing this init Flamingo, which it is actually inserting this graded cross attention in between these decoder layers, right? And we are inserting it every one layer. You can insert it every n number of layers, but in the ablation study they showed every one layer works good, but it is also more computationally expensive. Yeah, we set the new decoder layers to be the combination of gated cross attention and the original decoder layer. Now after setting up this Flamingo model, we set the entire model parameters to be frozen, like we freeze entire model parameter, and then we just unfreeze the perceiver resampler and the language encoder gated cross attention layers, right? So if you go back to this model, this is the model, right? So we have frozen everything except the perceiver resampler and the gated cross attention in the language encoder. Only those things will be learned. Right, so next let's just do the forward pass, and the forward pass will be the gradient accumulation rather than round robin approach like I mentioned. It first take the batch from Leon dataset, and again Leon dataset in this case is just a dummy dataset created from Coco dataset. Right, I can explain what happens is when creating the batch of each dataset is, for example, we have a sample. Since we are using the batch size of 2, we have two samples. For example, skateboarding blue shirt jumping down street stairs, and the other sample is a double-decker bus is driving along the street. First, we set the tokenizer padding to the right. On the right hand side, we do the padding. For the inference, we do it on the left. It's just how the autoregressive works. Because it wants to predict the next token, we want to, during inference, do all the padding on the left hand side. Then we have this sample, and what this pre-processing does is insert this image token. This is a special token, and a text and end of chunk, which shows that's the end of image text pair, right? So if we go here, the new sample becomes, we have the inserted an image token, we have some text, and then we have end of chunk, right? And then we also have this end of sentence token, which shows that's the end of the complete sentence. So this end of chunk denotes that we have the end of image text pair, and end of sentence is the end of the entire thing. Right, this new sample we pass to the tokenizer. Let's go through the tokenizer. Now what we have as an output as the input IDs, which are the tokenized text. And then we have some attention mask. The attention mask is one everywhere except here, where we have padded the sequences to make it equal length, so we can feed it efficiently to the GPU. And the one other thing we do is we set all the labels which are equal to pad token ID to -100, and all the tokens which are equal to media token ID to also -100. And the reason again is media tokens and end of chunk token are just special token to guide our model. We don't want to predict those tokens, right? And if you go to the official documentation of PyTorch, the cross entropy ignore index is -100, which means any label which is -100 will be ignored. So that's why we are setting it up to -100. And then we now do the forward pass. Again, it's doing the same thing. It is passing through the vision encoder, which we created, pass it through the receiver resampler. And this is being passed to the receiver resampler. Now where we are in is we are in OPT, causal large language model, and passing it through the decoder layer. But remember, we have modified the decoder layer to have gated cross attention and the standard decoder layers. So if we go through it, so it comes to this gated cross attention block first. It's a forward block of it. Then we get the logits. We pass it through our LM output head, which converts this logits to size of 2 into 16. 2 is the batch size, 16 is the sequence length, and 50,267 is the vocabulary. And now we calculate the loss, right? So again, this is the same as we had described before. The logits is everything except the last token. And since we want to predict, we shift, we take from the first until the end. So if at each point we are predicting the next token, and the loss is the standard cross entropy loss. Next we do the same thing for MMC4, and you can satisfy it does the same thing. I will not go to the entire thing. And then we do this combined loss, right? We combine the losses of both data set into one, which is essentially this equation, which is the sum of all data sets, and we are minimizing the expected value here. And then we do the backward pass, we step, and then we zero out the gradients, right? So this is the entire training loop. Let me show you how you can run it. So ideally, if you want to run it, you need to create this data set. You can run this Python create data set, and then you can run Python train or train.py. Maybe I have some debugging outputs like this 50,267. I should remove that. Okay, so this is training. I will stop it. I will now next go to the inference part. So I'm using pre-trained model, but this is how you can use this model to do the inference. For example, this is the input prompt. We give it an input image token, which is a placeholder for image, an image of 2 cats, which is showing an image of 2 cats, and then an image token, an image of bathroom sink, an image token, an image of, and the rest of that is completed by the model. So what this is, we load the model, same as we are doing in the training. We load these images, and the images are given in these links. So if I do this inference, it is running. It will first pop up and show some images. So this is the 2 cats, and we are given an input prompt, bathroom sink, and this is the query image. So we want the model to output what this is, right? So let's see what this will output. Again, taking a little bit of time because I'm running on CPU. I have very limited GPU memory. Right, so this is the generated text. So an image of 2 cats, an image of bathroom sink. So this is the input. And then finally an image of, and then this is created by the model of a Christmas buffet. which sounds reasonable, right? And end of chunk. So the output is a Christmas buffet. Is good. Okay, that's it. That's how Flamingo works. Again, all of this code is in the GitHub repo.